So we are going to see some examples to illustrate the method of Lagrange multipliers, where to find the extrema of a function f subject to this constraint g. Okay, so what our procedure is this, that if these extreme values exist and the gradient of g is not equal to 0 on anywhere on the condition or the surface that is given by that condition, then what we do is we create an equation by connecting the gradients with a multiplier called lambda and incorporate the condition. And if we find solution points here, then we will go ahead and compare the values of the function that we have to optimize, okay, at those points. And the maximum is maximum of those values will be the max and the minimum will be the min. Okay, so we are going to work on this example that we have to maximize this function, which gives the distance from the origin, square of the distance from the origin of any given point, subject to what? Subject to this condition. Actually, the condition was given as this, and I just went ahead and defined g to be this function. All right, so we may say subject to g equals 0. All right, so let's proceed with our method. Let us proceed with our method. That is, we shall create equations given by this condition, that gradient of f is lambda times gradient of g. Now f is x squared plus y squared plus z squared. So what the gradient would be? That will be 2x, 2y, 2z. All we do is take the partials of the coordinates with respect to x, y, and z respectively, right? Same thing we will do with this here. So that is going to be how much? 4x cubed, okay? Then 4y cubed. Pardon my writing like this, okay? All right, so y cubed, all right, and then 4z cube over here, okay? So here I'm just replacing this by z, so we get 4z cube, and what is that going to produce for us? That will give us that when we compare the components, we have 2x equals 4 lambda times x cubed, right? Okay, x cube, all right. And then we have another equation. I'm just going to use this to write that equation. So here we have y, and the third equation is very similar, okay? That is the same equation. The only thing is that it's in terms of z, okay? So now let's look at these three equations. Now we have to say we want to eliminate lambda among these three equations, okay? One problem that will come is when x or y or z is 0, because then we get the equations 0 equals 0. So what we would do when we are analyzing something in this manner, that we will split it in cases. So notice this here first, that we cannot have all x, each of x, y, and z equal to 0. Why? Because we have, our condition is what? Our condition is this, that this has to be 0, which is not possible if all these are 0. Okay, so we'll just say that it is not possible, right? Okay, very good. All right, now case 2 is, so we have three variables. So let's just assume that, say, let's start with this. Exactly one of these, say say x is 0, okay, and we will see whether y and z, they produce a similar scenario when we go to them or not. So say x is equal to 0, right? Okay, and then we have the other two, that means y is not equal to 0 and z is not equal to 0, right? Okay, so here we go. So this is the situation we have. So if we have this condition, then we are going to ignore this equation here, the very first one, and going to use these two. Okay, so when we are using these two equations, what does this tell us? This or these two together, what do they tell us? If you look at the value of lambda, it's going to be 1 over 2y squared. So it gives us that lambda equals 1 over 2y squared, and we could take y to the denominator for a simple reason that it's not equal to 0, right? And this equals how much? 1 over z squared. And what will be a consequence of that, or what will be an implication of that, is that y square and z square are identical, right? Okay, so by eliminating lambda, we got this, and then what we are going to use is, we are going to use the third condition, that this quantity is equal to how much? This quantity is equal to 0, right? Which is which says what? Which simply says that we have x to the 4 plus y to the 4 plus z to the 4 equals 1. And since y square and z square are identical, y to the 4 plus z to the 4 will be the same, and x is 0, right? So what will this give us? Let's just write it, since we have a space, because I'm talking too much, not writing much. So here we get a 0, right? Okay, and just takes a few seconds to write all of it out. So we get this, and since y square, z square are identical, what will this give us? We may say y to the 4 plus y to the 4 is 1, which means, that means what? 2y to the 4 is how much? 1. So that means that y to the 4 is 1 over 2, right? And we are, remember this, we are interested in x square plus y square plus z square, right? So first let's see what y square is, sorry. Okay, so y square is how much? Simply 1 over 2 to the 1/2, right? And by 2 to the 1/2, let's assume that we are meaning the principal square root, and that is going to mean what? That y is going to be how much? Plus or minus 2 to the 1/4, right? Are we clear? So this is this, and along the same lines, if I let this become z to the 4 plus z to the 4 equals 1, what shall we have? We shall have, as a consequence of that, we shall have simply z equals 1 over plus or minus 1 over 2 to the 1/4, right? So what do we get as the, as set of points as a result of this? Remember, x is 0, so we may take both these values as positive values, all right? Okay, or we can do this, combine them with one of them being negative, right? And then here we can make this negative, right? And then we can make both these guys negative, okay? All right. And similarly, say we had taken y equals 0 instead of x equals 0, right? So in that case, which points shall we get? We shall get, so if y is 0, we'll just get this here, right? Comma, okay. And then I can just bring them all here and just change them quickly, right? So here we got this, right? And then we got what? Got this, and we got that, and then we have a possibility that our who can be 0 then? Z can be 0, right? So we will just move 0 to the third coordinate. So how many such points do we get? We get 12 such points, and I'm just speaking and talking at the same time. And what you can see is that the way the points are, since we are trying to find max or min of x square plus y square plus z square, all the values will be identical at these points, okay? So say for instance, we are, so we have to do what? Look at the values of the function f, which is x square plus y square. Okay, where is that? Y square plus z square, right? Okay, and again here we got x, y, z equals that, right? And that is going to be, say I take the very first point, so that will be 0 square plus, what's the square of this? 1 over 2 to the 1/2, or square root of 2, right? Then plus, then plus the same quantity again. So what do you have here? You got 2 over 2 to the 1/2, which is simply 2 to the 1/2, or you may write it as square root of 2 if you would like. All right. Okay. All right. Good. So sorry, I'm just taking too long in doing these routine calculations. So this was the case 2. So now let's just take the case 3, where we would say, let's just scroll it a little up, okay, that exactly 2 of x, y, and z, okay, are zeros, okay. Then so in this case, let's do this time. Last time we killed x, so now let's be fair in the calculation. We will go ahead and let these two guys be 0, okay. So they are zeros and x is not equal to 0. So we are not going to need our Lagrange multiplier here. Why? Because remember the condition that we have. The condition is this. We can directly substitute x to the 4 in this equation, right? Because x is not equal to 0 and these guys are zeros, right? So what do we get? Those guys being, y and z being zeros means these are out, okay? So x square is 1, right? So we got x square as 1. And then what? X as plus or minus 1, right? Okay. So which points do we get as, because of this 1, 0, 0, negative 1, 0, 0 I meant, and then positive 1, 0, 0. Now in case we had this, say x and z were zeros, okay, then what will happen? All that will happen is this, that these guys will just shift in the middle, okay, by similar calculation, okay. And in case we have this, that x and y are zeros, then these will just move to the third place. So I think here we will get only 6 such points, okay. All right. So if we look at our function that we had to maximize or minimize, that is f of x, y, z, okay, just bringing it again and again. By now we must have memorized this objective function, right? X square plus y square plus z square, all right? And what happens if any of them is 1, the other two are 0, this is simply going to become 1, right? Now let's move to the last case, and I did not take my cases in a very good order because remember, see, I started with exactly 1 being 0, exactly 2 being 0, and I already ruled out that all three of them cannot be zeros, right? But anyways, we have one case left, that is none of them is a 0, right? None of them is 0. So in that case, what will happen? Remember this, all the equations, all the three equations will play a role. Let me recall those three equations for you. I don't think that you did not remember that. Okay, so here. So since none of them is 0, what will this indicate? That x square and y square and z square are the same when we eliminate lambda from among them, right? Exactly as we did before. So what we have then, that x square equals y, sorry, equals y square, and that equals what? Z square, right? And when we apply them, when we apply this condition that we, or this constraint that we have, then what do we get? We get the following. That is, since they are all the same, so I can just replace them by just one of these, right? Okay, so we got this. Okay, all right. So say I'm replacing them all by x. So we get, what do we get? 3x to the 4 is 1, right? So what shall we have eventually now is that, well, let's just go in order. No need to rush. You can fast forward if I am getting too boring for you. So this is 1 over 3 to the how much? 1 half, and that will give us x as what? Plus or minus 1 over 3 halves, and I don't, I clicked it wrong place there. Okay, and similarly y and z will have the same values. Okay, so y is the same, and then z is the same, right? Okay, sorry about that. Okay, good. So what are we going to get? We are going to get a set of how many points? I think 8 points, right? That is 1 over 3 to the 1 over 2, 1 over 3 to the 1 over 2, these, right? And then we can do this, make them like, make this one negative, or do what? Make this one negative, or make this one a negative, right? So here we got those combinations, and then what we will do now is, well, let's start making this. Say these two are negative, or these two are negative, or these guys are negative, right? Okay. And then what we get, the last condition would be that all of them are negative, right? Okay. So we had 8 possibilities, and we got all 8 of them, if I'm not missing any. And now, if I compute this, okay, fx squared plus y squared plus z squared, then what are these guys? They are simply squares of, no, 1 second, what did I do wrong? Okay, I did this wrong. Man, I can't believe I did that to you. I'm sorry. This is 3 to the power, what? 1 over 4, not 1 over 2, 1 over 4. Okay, let me fix these and come right back to you. Okay, so here I cleaned up my mess. All right, so what happens here is we get this is squared, right? And then a square of the same quantity again. Okay, so squared and squared. So what shall we get? 1 over 3 to the 1 half. And how many of them? 3 of them. So 3 over 3 to the 1 half, or simply, let me just simply write it as a square root of 3. So what are the possible values? We got a square root of 3, a value at these 8 points, one as a value of these, how many? 6 points, right? And a square root of 2 as the value at those 12 points. So I think our max is square root of 3, and our min is how much? 1. Let's just go ahead and very quickly look at these graphically. All right, so I'm just going to create a Matlab graph and show it to you. Okay, so what I did was I already created a live script for you. Okay, this is for the minimum values because so I'm making a level surface corresponding to the minimum value, and this is your condition, x to the 4 plus y to the 4 plus z to the 4 equals 1, and this equals 1 is minimum. So what should these level surfaces do? They should just have common tangent planes or common normal lines at these points. Okay, and I have posted the script, you know, along with a description of the video. And so what happens here is, come on, where are you, the graph? Okay, yes, here is a graph, and the trouble is this, that I don't know how to make it transparent. Okay, so how about this? We just go ahead and cut the graph in half, because I've already spent so much time that I don't want to really spend time in learning how to make that transparent. I would do it another time. Okay, so there we are. So we got this. Let's just get the graph again. All right, so it's coming up. All right, I should have probably waited for it to come up, but anyways, come on, please. Okay, so here it is. Okay, let's take it into the figure window. Okay, come on, please. Okay, okay, all right, it came on a different screen. Let me bring it in for you. All right, so what we see is this, that if we go ahead and look inside, okay, all right, I thought it was going to rotate it for me, okay, so, but it's not doing that. Let me try it once again, rotate 3D. Now it's going to do that. Yes, here it is. Or maybe I'm overheating this computer, right? Okay, so here, well, just trust me, these are, come on, stop, please. Okay, so what we got here is, man, okay, all right, there is a lag, okay, here. So we got, 4 of these points here. One of them is there on the top, okay. When I try rotating it, it's just taking a little bit time because my computer is probably not that capable, okay. And then the lower half is going to give us only one extra point. So, that's that one. So we can see we have common tangent planes, or maybe if we look at the max, we might have a better picture. Now let's go for the other condition, okay? And all I have to do here is, remember, our max is the square root of 3, right? Pardon me. Okay, so if we go ahead and graph it, all right, then in that case, if you remember, we had 8 points on which it is supposed to produce the maximum value. So let's see how many do we see. Okay, I'll just take it into the main window again. Okay, and bring the window here. And this time after dragging it, I'll be patient, okay, because I know my computer is not that good to run so many things together. Okay, so we are looking at the max, okay, all right, good. So now see, patience paid, right? Okay, so what do we have is, okay, come on here. So we have these guys. I think here it would have helped to see the, it be in a transparent mode. You can see a point of contact is here. I mean, you can't see it because I couldn't make it transparent, but they have 4 points of contact on the upper half, then there will be 4 on the lower half, all right? Okay, and then you can learn on your own how to make those transparent. And at those 8 points, we have common tangent planes, all right? So I don't think that many of you are still with me. Just to show you the points of contact, I went a little stubbornly and and limited it into the first octant, and then just brought this up, and you can see the point of contact here. And let's look at the tangent plane. And for the tangent plane, what I would do is that I shall create the tangent plane on the surface that is given by this condition, and you will see that is the tangent plane to the sphere that is created by the function that we had to maximize. Okay, so let's calculate an equation of the tangent plane. What we want to do is that we want to write an equation of the tangent plane to this surface at which point? The point that was, the corresponding point in the first octant, right? Okay, so here we go. So this is an equation, right? Okay, so what we will have, we will take the gradient of this function formed by this at this point. So let's quickly do that. We know what the gradient is. 4x cubed, okay, 4y cubed, and then 4z cubed, all right, which is, we can factor 4 out, and gradient simply gives us the normal vector, so we may not bring the 4 in. And so by the cubes, what we will mean, this to the power 3/4, and the same thing all over. All right. So what we got is this, that this is a normal vector at this point, right? So an equation of the tangent plane would be what? What that would be is, this is the first component of the normal vector, okay? And then x minus this quantity, right? Okay. All right. Then plus the same thing with y, okay? All right. Plus the same thing with z. And the reason I'm computing the or calculating equation of the tangent plane at the condition is because we can see that the tangent plane is common to the sphere as well. Or maybe I'm doing it this way because I'm just too tired right now. Okay, so what this would be, this times x plus this times y plus z, and we can multiply these. Notice this, what we have, 3/4, 1/4. When they multiply, they will become -1/3. So we'll get 3 -1/3. They will add up to a 1, right? So what is an equation of the tangent plane? X plus y plus z equals how much? 3 to the 3/4. All right. So we brought the equation of the tangent plane over here, or created this quantity, or sorry, this function, and then we'll set that equal to 0, and let's see what they all together give us. Okay, and let's let the graph come up. Okay, and we are almost there. Okay, and here you can see, or we can see it in the bigger region. Okay, so here I had created the tangent plane for this surface given by the condition, and you can see that it is a tangent plane on that surface given by that maximum value of function as well. So thanks for staying with me so far, those of you who did, and including myself. This was just too